Let us start with the first lecture of Astrophysics 1 special paper, which is known as DSC from this semester. So before we begin, let me distinguish between the words astronomy and astrophysics. Astrophysics is part of astronomy. Astronomy actually refers to the study of anything and everything that lies beyond our atmosphere, that is the Earth's atmosphere. And whatever objects are there beyond the atmosphere of Earth, those are all astronomical objects. And when you are studying some particular process that is happening in the astronomical object, basically when you are doing physics of astronomical objects, that is called astrophysics. uh, and there are other parts in astronomy like astrometry, where you are basically trying to position objects in the sky, or you're trying to measure their position, etc. And astrology is, something that lies beyond science, and we'll not talk about that, and I hope nobody talks about that. So let us begin. In today's lecture, we will be covering some brief introduction to astronomy. Eventually, we will get to astrophysics also, but initial few lectures we will be adhering to the astronomy part, or basically the astrometry part, where we are talking about how to observe things, etc. So let us go to the first slide. So what you can see in this slide is, if you look beyond the writings, the background is actually a starry sky that you can see. If you go over to some, very remote location, like say some desert, in the night sky over a desert will be something like this. Actually, not so many stars, but if there is a very good visibility, and if you look through a telescope and piece together all the different portions of the sky, then you will see so many things. And all these tiny light specks are either stars or galaxies, and some things are nebulas. You can see one, this ray, which is basically something like some meteorites. These are some constellations. This probably is a galaxy. And all these tiny dots, these are big, usually most of the things are actually galaxies. So the universe is actually filled with galaxies, and what you can see normally every day in the night sky are actually lights from stars. And all these background tiny specks we cannot see because of the light pollution of our locality, because all the street lights and city lights, they actually pollute the night sky, and these things are called light pollution. So if we go to a place where there is no light pollution, then probably we will see all these tiny specks, and most of these are actually celestial objects beyond our own Milky Way galaxy, and most of these are lights from other galaxies. And since these galaxies are so very far away, so we do not see lights from individual stars in other galaxies. We see those galaxies as a whole as tiny dots of light. And there are certain stars also which are actually within our galaxy. Individual stars we can see only from our galaxy, and the other dots are usually galaxies or nebulas or some such other astronomical objects which are not stars. By stars, what we mean is gaseous bodies which are bound by self gravity, and the main energy source in these bodies are usually internal. That source can be nuclear or gravitational most of the times, and they are usually made of hydrogen, helium, and some trace amount of heavier elements. There are stars which are made of only hydrogen. The very first generation of stars, which were the first stars that were made in the universe, that consist of completely hydrogen. And then probably you know from general knowledge that these hydrogen atoms usually fuse together to process energy in the star, which are actually the source of energy of stars. And this fusion of hydrogens actually make this helium atoms. So when a star is, as the star grows old, there is more and more helium at the center of the star. Okay, and eventually these stars actually explode and destroy themselves, and then there is hydrogen and helium in the universe, and those hydrogen and helium again come together, and then they make next generation of stars. And those second generation of stars will also have helium along with hydrogen, and so on. There are other stars, heavier stars will make other elements also while exploding, and so on. But these things are the portions of stellar evolution that we'll do later on in this course. But for the time being, let us plow on with the initial basic things. Because these stars are bound by self gravity, and self gravity normally works in a radial direction, so stars are usually spherical shaped. But if the star has a lot of significant rotation around its own axis, then because of that rotation, there will be some shape shift, and they will look like spheroidals. Like this star Acner, it has a quite significant rotational motion, like 230 kilometers per second. It moves around its own axis. So the closest star that we have is, of course, the sun, which is nearly 1.5 into 10 to the power 8 kilometers, that is 15 crore kilometers away. And this Earth Sun distance, this is actually the average Earth Sun distance. We know that any gravitationally bound object actually moves around in an elliptical orbit, but Earth's orbit around Sun is very nearly circular, so it has very small ellipticity. So this is nearly 1.5 into 10 to the power 8 kilometer, and this average distance is called, sometimes it is a bit more than this and sometimes it is a bit less than this, and this average distance is referred to as one astronomical unit. This is our first distance unit that is defined using our astronomical objects, that is Earth Sun distance, and this is a very standard definition of distance. We, while talking about astronomy and astrophysics, we do not really talk in terms of kilometers, because then we'll have to deal with too many 10 to the powers and all that, and eventually you'll see we'll talk about some other units of distance like a parsec, which will come a bit later in the course. So this sun is our closest star, and all whenever we are talking about different stellar parameters like mass of the star, radius of the star, and this is luminosity of the star, temperature, effective surface temperature of the star, or pressure of the star, we usually refer to solar values. And for those standard reference values, we use this circle with the dot at the center. So m sun is the solar mass, this is a solar radius, solar luminosity, and so on. So whenever we talk about mass of some other star, we actually tell you the ratio of that star's mass with respect to sun's mass. This way, actually, you will see when we do astrophysics, most of the formulas are written in reference to solar values. Now the next neighbor, that is our nearest neighbor after sun, is called Proxima Centauri. It is nearly 4.24 light years away. You know what a light year is, the amount of distance light particle can move given a 1 year time. The 1 year time, if you convert them to second, is actually this value, 3.15 into 10 to the power 7 seconds, and this is your light speed. So multiplying them, what we get is nearly 9.5 trillion kilometers. I'm referring to kilometers for the beginning of the course, but eventually we'll talk about astronomical units and parsecs, etc. only. So approximately 100 to 400 billion, that is 10 to the power 9 stars. 1 billion is 10 to the 9. So nearly 400 billion stars are there in our own resident galaxy, which is our Milky Way galaxy. And there are several other galaxies where around this number of stars are usually there in standard galaxies. So let us move on to the next slide, where we are talking about some, let us talk about some solar parameters. These are for references. So mass of the sun is nearly 2.2 into 10 to the power 30 kilos. Radius is nearly 7 into 10 to the power 8, 10 to the power 8 meters. Notice that though there are too many decimals and all these things, but when we are talking about astronomical objects, we don't be very fussy about the actual, we don't get very fussy with the numbers. I mean, 1.99, you can approximate it as 2, 6.96 you can write 7, 3.83 you can write nearly as 4, doesn't really matter. The temperature, you will see 5780 in some books. In some places, you will see that this is written as 6000 Kelvin, and so on. There is no point fussing around these values, because the 10 to the power thing is way too high, right? Then again, the age. This is age of sun, which is nearly 4.5 giga year. 10 to the power 9 refers to giga, so this is a giga year. Then the central density, that is the density at the center of the sun, is nearly 150 grams per cc, or per cubic centimeter. And if you, work it out in terms of kg per meter cube, is like 1.5 into about 5 kilos. Then the central pressure is like this value, 2.29, that is nearly 2.3 pascal into 10 to the power 16 pascal. Now 1 pascal is the basic definition or the basic unit of pressure, and we usually talk about atmospheric pressure. When we say ATMS, this means atmospheric pressure at Earth's sea level, right? So that is 1 atmospheric pressure, and that amount is basically 1,01,325 pascal, which is nearly 1 to the power 5 Newton meters. 1 pascal is basically Newton per meter square. Newton is your force unit, so 1 Newton per meter square is 1 pascal. So this many pascal gives you 1 atmospheric pressure. Since it is 2.29 into 10 to the power 16, write it in terms of atmosphere, it will be like 2.27 into 10 to the power 11 atmospheric pressure. So the central pressure of sun is pretty high. The average density of sun, as you will see when we do the calculation, you will see the average density inside sun is like that of liquid water. But though The material of the sun is not in a water or liquid state, it is in a plasma state, but that will come in a later lecture. Again, the central temperature in sun is 15.6 into 10 to the power 6 Kelvin, so basically nearly 15 million Kelvin. Notice that the mass, radius, luminosity, and effective temperature of the sun, these are the quantities or parameters that we can measure directly. So these are directly observable quantities, whereas this age of the sun, central density, central pressure, and central temperature, we can estimate or we can compute from indirect way. And the central density, central pressure, these things we cannot measure or compute directly. I mean, we can compute by using very intricate numerical modeling of sun, but very approximately we can actually do very minimal amount of back of the envelope calculation, very easy calculation to estimate the central density. So that is, estimate means we can estimate what is the maximum possible central density of sun or maximum possible pressure of the sun at the center, what is the maximum possible temperature at the center. These things can be calculated very easily using just half a page calculations. Analytical calculation will tell us these values. So let us go to the next slide. So now let us talk about locating stars in the sky. As you know that since stars are very far away from us, because of this great distance, we do not really see stars move in the sky, not in a day-to-day basis. And even if we try to locate the star's actual motion in the sky, we'll have to wait for many years to see it move a little bit in angular position. So the star's actual motion we don't really see, but we see the stars move in the sky basically because of the motion of earth. As earth moves around its own axis, so every day sky rotates in the opposite direction, so the whole sky rotates, and all the stars or all, any not just stars, any stellar object appear to us like they are stuck on the inside of this hemisphere. So to assign positions to them, we can use spherical polar coordinate. Like there are 2-3 different ways, or actually quite a few different ways to assign these coordinate values, these angular coordinates. There is no point trying to describe them in terms of radius and two angles, because radius is for different stars are at very different distance from us, but since human eye cannot distinguish a great depth, so all of these stars appear like they are at the same distance. So basically some kind of infinite radius hemisphere or some constant radius hemisphere. So we will talk about two angular coordinates. These angles are measured in several alternative ways. Just imagine that when we are moving around on earth, we have a nearly constant radius, and the two angles with which we distinguish locations on earth are your latitude angle and longitude angle. Now how do we measure this longitude and latitude on earth's surface? See, the longitude is measured starting from Greenwich and latitude is measured starting from the equator, right? So we'll have to define from which point we are measuring which angle, defining the perspective with which we are making this spherical surface or considering this spherical surface gives us primarily two different type of things. One is Altazimuth system and another is equatorial system. There are also other systems like galactic system and supergalactic system, etc., but we will not talk about those in our course. Angles are usually, you know that angles are measured in degrees and arc minutes and arc seconds, etc., but actually in stellar objects, since they are very far away, so their angular separation between two stars can be very small. Even one arc second is a big angle in the sky. So we'll usually talk about milli-arc second or even micro arc seconds when we are talking about angular separation between two stars. See, these are the two stars, and if you are looking like this, your point, line of sight to this star and this star, the angle between them are called the angular separation between two stars. And when we are talking about, say, the moon, the two sides of the moon, the line of sight are different for the two sides, and the angle between them will give you the angular size. The same angular kind of measurement uh, we are making. So for reference here, let us say the moon and the sun both are actually half a degree in our sky. Let us move on. So just for a ready reference, a handy guide is for angular measurement in the skies. If you stretch out your hand in front of your face like this, like this here, then your closed fist actually measures something around a 10 degree. This will vary slightly from one human being to the other, but roughly you can say that one closed fist is 10 degrees. Similarly, your little finger width of that angular width, when your hand is in this kind of a stretched position, the width of one little finger is like nearly 1 degree. Width of this the index, middle, and ring finger they together they make 5 degree, and index and your little finger, their difference is 15 degree. And if you stretch out your palm, the index, the thumb and your little finger, the distance is roughly 25 degree, and so on. So this is a handy way to measure the width or the angular separation of objects in the night sky. Let us also talk about constellation. Since remember, I have talked about I have said that stars are stuck in the sky, but because of Earth's rotation, to us stars appear to be moving around a lot. Any stellar, any celestial object, any light spot that is there in the sky, we see them move around a lot. All these stars or any stellar object appears as dots of light. It is difficult to distinguish one dot from the other, right? How do we track the motion of these objects? So to distinguish these things, in very ancient times, people came up with the idea of drawing patterns among stars. Since these stars are stuck in the sky, so if we can identify patterns among these stars, then the patterns move as a whole. For example, see these group of stars here, they are making a pattern. If we connect them with imaginary stick figures, this is a pattern. This is called a big dipper. Similarly, if we look at these stars, they are making another pattern. This is called a small dipper, right? Again, then look at these stars. This is 1, 2, 3, 4, and this 5. They make this thing. This is called Cepheus. Similarly, there is a W kind of shape which is called Cassiopeia here. So these are all patterns which, due to the motion of Earth, moves. Like actually, the whole sky moves. So all these patterns move in tandem. And if we can recognize these patterns, so we can recognize these stars wherever they are in the sky. At different times of the night, your sky looks different, right? So we need these patterns to identify individual stars, and these patterns are called constellations. The International Astronomical Union, they have divided the whole observable sky into 88 such constellations, and each constellation is assigned certain area around them, and the whole sky is divided into these constellations. Let us say I want to locate a star called Rizal. Then I know that the Rizal star belongs to the constellation Orion. By recognizing the pattern in the sky, I'll directly go to the Orion constellation, and within that constellation, I'll try and look for the particular star Rizal. Let us remember that members of a given constellation only appears to be close to each other in the projected plane of the sky, but their actual radial distance from us or from each other may vary greatly. This is because human eye is incapable of distinguishing different depths at a great distance, and therefore the whole sky appears to be at the same distance from us, and therefore the sky appears to be hemisphere to us, and all the stellar objects appear to be stuck on the inside of that stellar sphere. Apparently all of them appears to be at the same distance, but their physical distance from us are different. And naturally, these constellations are not gravitationally bound systems. That is, these stars are not interacting with each other gravitationally. So this will be clear if we look at a given example of Orion constellation that is visible in the northern hemisphere. You can very easily identify the Orion constellation in the sky. Try for yourself and see. In this slide, let us see, this is the Orion constellation as it appears to us in the plane of the sky, and on the right hand panel you have the actual position of the members of the Orion constellation at different distances in the actual three-dimensional space. So you see the three members in the belt of the Orion, these three stars like Alnitak, Alnilam and Mintaka, these three are appearing quite close to each other, but in reality they are actually very far off from each other. One is probably at 650 or something light years, one is at 700 light years, and the farthest is actually this central one, Alnilam. This is nearly at 1350 or 1342 light years as far as I can remember. The belt of the Orion is actually a nebula. This is not a single star, this is a star forming region. That is why it is overall well lit. So this is a nebula, and this is called Orion Nebula. This is nearly again that 1300 light years distance mark. So the other stars are like this Betelgeuse here on the top. This Betelgeuse is the brightest as it appears to us. The second brightest of our constellation is Rizal. the third brightest is Bellatrix, and so on. So these names, this Betelgeuse or Rizal or Bellatrix, or these strange names like Alnilam, Alnitak, Mintaka and Saif and Maisha, etc., these are all, most of them are Arabic names because these names were given by ancient Arabian astronomers. But in order of their brightness, we can name them as Alpha Orion, because Betelgeuse is the brightest as it appears to us. So Betelgeuse is called Alpha Orion, then Rizal is called Beta Orion, then Bellatrix is called Gamma Orion, and so on. So we just name them as alpha, beta, gamma members of a given constellation. This is not just for Orion. For any given constellation, the brightest of that constellation member will be called alpha, followed by the name of the constellation, and similarly second brightest will be beta, followed by the name of the constellation, and so on. Let us now move on to the next slide, which is on zodiac. What is zodiac? Zodiac are a family of constellations that appear around the ecliptic of sun in the sky. What is ecliptic? Ecliptic is the Earth's trajectory around sun projected onto the sky. Once again, ecliptic is Earth's yearly trajectory around the sun. When you project that trajectory onto the celestial sphere, what you see is the ecliptic. We don't see Earth's trajectory because we are standing on Earth itself. What we rather see is the apparent trajectory of sun around Earth. Since Earth is moving around sun, what we see standing on Earth is that sun is apparently replicating that motion. So when Earth is here in the month of May, you see sun here, and behind sun you will see the constellation Aries. That is, just after the sun sets in the evening, what you see in the sky is the constellation Aries. Similarly, in the next month, say June, Earth has moved a bit and appeared here, and correspondingly the person standing on Earth will see sun has moved here in front of the constellation Taurus. Similarly, in July, sun will appear to be in front of the constellation Gemini. This way, as in the course of the whole year Earth moves in this elliptic path, the person standing on Earth will see sun moving in that elliptic path in the same orientation, and as the sun moves in the sky, people on Earth will see sun moving in front of different constellations, and this will keep happening throughout the year. So 12 such constellations are there which will appear in the background sky behind sun throughout the year, and these 12 constellations are called the zodiacs. Actually, the month system that we have refers to this positioning of 12 zodiac. Remember that there are many other constellations in the sky, but these are the 12 that appear along the plane of Earth's orbit. So much so for the zodiacs. Let us now move on to assigning coordinates to stellar objects. So how do we do that? See, the dome of the sky appears as half sphere because the other half is actually hidden by the ground. So these two halves put together is called the celestial sphere. So since it's a sphere, any stellar object that appears in the sky will be positioned using the spherical polar coordinate, and the constant radius of the sphere will of course be arbitrary because that radius is not a physical radius, it is actually the apparent radius, which is because of the incapability of our eye to distinguish depth at great distance. The other two coordinates on the sphere, which are the two angles. Just remember the spherical polar coordinate we have. What we have in spherical polar coordinate is one xy plane and the z axis, and we measure the angle on the xy plane starting from the x axis and going towards the object, and the other angle is measured by starting from the z axis and coming towards the xy plane. So these are the two angles given by phi and theta. We will use this same coordinate system. All we have to do is we have to choose a suitable xy plane and a suitable z axis in context of celestial sphere. How do we do that? We can do that in several different ways. One of the primary ways is with respect to the observer's perspective. This is called Altazimuth system. The other system is based on Earth's rotational axis. That is, the z-axis of this system will be Earth's rotational axis, and the equatorial, the xy plane will be Earth's equatorial plane. So this is called equatorial coordinate system. There are several, quite a few other coordinate systems also, like galactic coordinate system and supergalactic coordinate systems, etc., which are important when we are observing the dynamics of a galaxy and so on. Another point to remember is that what we see in the sky depends on which date of the year you are observing, which time of the day you are using to observe, and also your latitude and longitude on Earth. Since what we see in the sky depends on these things, we can reverse the argument and say that we can use position of a known star in the sky to navigate on Earth. If we know the position of a given star and we know when that star should appear where in the sky, then just by identifying that object in the sky, we can extract the information on the latitude and longitude of the observer, right? That is, we know where the star in the sky, we know what date and time it is. Since using this the position of the star can be found, so in reverse, knowing the position of the star and using this time and date, we can extract the information about latitude and longitude of the observer. In ancient times, the sailors in the sea used to do this trick to find their way around while sailing in the sea. So let us now start with the Altazimuth coordinate system. This coordinate system is completely based on what an observer sees in the sky and how he is positioned himself. Let us say you are standing in the middle of a ground, so your own body forms one axis. That is, if you imagine a z axis from starting from Earth's center through your body towards the sky, then that axis, your body axis, touches the sky at a particular point which is exactly on top of your head, and that is called zenith point in the sky. The corresponding point that is just down below your leg on the other side of the sky, that will be called nadir point in the sky. Nadir point we cannot really see, but this axis or your body axis forms the z axis of the spherical polar coordinate, and this plane or your horizontal plane is referred to as the xy plane. If you use a compass, then the compass will show you what is the north direction from you, so that is your north direction, and if you stand facing the north direction, your right hand side will show you the east direction, your left hand side will be the west direction, and your back of your head is the south direction. So this is the basic perspective of a Altazimuth coordinate system. Now let us move back onto the previous slide where we are showing the system itself. So imagine yourself standing here, your body axis to your head is touching this point in the sky, so this is your zenith point. So around you, this is your horizon and this is your horizontal plane, right? Compass shows you a north direction, so that is your north direction, and completely opposite side is the south direction. This corresponds to your xy plane, this is your z axis. So therefore, you measure the phi angle or azimuthal angle starting from the north point. North is our reference 0 for azimuth value. So azimuth is the angle which we measure along this horizon, and we go towards east for positive values and towards west for negative values. Altitude is what we measure from the horizontal plane towards the zenith, right? This way. So altitude is angle above the horizon to an object. So let us say here we have an object in the sky. So what will be its altitude? Altitude will be measured starting from the equatorial plane towards that object along the meridian. What is meridian? Meridians are great circles which you can draw over the celestial sphere. So all these arcs are meridians in this picture. Among them, two are of particular interest to us. One is this one, the observer's meridian or the local meridian. This is defined as that great circle which connects the observer's north point, that is 0 degree azimuth, to the observer's south point, that is 180 degree azimuth, of course to the zenith. And the other important meridian is the object's meridian, which connects the zenith and the nadir of the observer but goes through that particular object that we are interested in. When we are measuring the azimuth of, say, this object, then we are starting from the observer's meridian, we are going towards the east direction through the equator all the way towards the object's meridian, and this whole angle is the azimuth angle for this object. And of course, altitude is measured from the equator line, that is this line, northward or southward, and it is measured along the meridian of the object. One thing we need to remember is all meridians are lines of constant azimuth angle. Let us now move over to the equatorial coordinate system, but before we do that, let us briefly remind ourselves of the coordinate system on Earth. So basically the latitude and longitude system. This is probably familiar to you from your geography lessons in your school. So latitude are the angles which are measured from equator towards north or south. So equator itself is the 0 degree latitude, and all other smaller circles which run parallel to the equator are lines of constant latitude. So latitude angles are equivalent to the theta angles that we do on spherical polar coordinate. but instead of measuring the theta angle starting from z axis towards the xy plane, we rather do it starting from the xy plane or the equator towards the z axis. Before we discuss longitude, let us notice that all these vertical lines that start from Earth's north pole and go over to Earth's south pole, these vertical lines are called meridians. These meridians are not to be confused with the meridians that we talked about in connection with Altazimuth coordinate system, because those meridians were lines going from observer's zenith to observer's nadir on the celestial sphere. But here when we are saying meridians, we are referring to meridians drawn on Earth's surface, and these meridians are starting from North Pole and going over to the South Pole. Among these meridians, this particular one, which is going through the Greenwich area, is called the prime meridian. Let us now discuss longitude. Longitudes are nothing but phi angles of the spherical polar coordinate. These are measured along the equator, and all these meridian lines drawn on Earth's surface are lines of constant longitude, and we measure it starting from the prime meridian. So prime meridian is defined as a 0 degree longitude, and as we move right or left on the equator from the prime meridian, those will give you different longitude value. East of prime meridian is positive and west of prime meridian is negative. So notice that distance between lines of constant longitude depend on latitude. The physical distance between two constant longitude lines is greatest at the equator. But as we move to higher and higher latitude values, the distance between two constant longitude lines decrease, and the distance completely vanishes at the north point. Also notice that location of prime meridian, that is the meridian through Greenwich, is arbitrary, and there is no fundamental reason why this is taken here at Greenwich, but this is purely a matter of choice. So let us now move over to equatorial coordinate system. This is based on Earth's axis, that is Earth's axis of rotation, and Earth's equator. What we do here is we extend Earth's equator out to the celestial sphere, and it is the reference plane for measuring an object's position above or below. That is, this equator on the celestial sphere or celestial equator is giving you the equivalent of xy plane of the spherical polar coordinate. This is of course a great circle. So north celestial pole and south celestial pole are nothing but projections of our north pole and south pole of Earth. So we can say that these are zenith of north pole and zenith of south pole. Notice that it is not nadir of south pole. As we live on Earth, the projection of Earth's orbit around the Sun on the celestial sphere appears to us as Sun's yearly track in the sky. This apparent yearly track of Sun in the sky is referred to as the ecliptic, that is this line. As the plane of Earth's orbit around Sun is at an angle of 23.5 degrees with respect to the celestial equator, so the ecliptic also appears at an angle of 23.5 degrees with respect to the celestial equator. Naturally, there are two crossing points of the celestial equator and ecliptic on the celestial sphere. They are called the vernal equinox and the autumnal equinox. Vernal equinox is when Sun crosses the celestial equator from southern hemisphere towards the northern hemisphere, and autumnal equinox is when Sun crosses the celestial equator from northern hemisphere towards the southern hemisphere. The highest point that the ecliptic reaches on the celestial sphere is called the summer solstice, and correspondingly the lowest point that Sun reaches, or the Sun's track reaches, or the ecliptic reaches on the celestial sphere is called the winter solstice. So we measure the two spherical polar coordinate angles, that is theta and phi, with respect to this equator. One is phi angle, which is measured along the equator starting from vernal equinox towards the summer solstice, then autumnal equinox, finally winter solstice, in this order. That is, right ascension is the angle that we measure starting from vernal equinox going towards east. That is, we start from vernal equinox, which is around March 21, when Sun's motion crosses celestial equator at this point. This is the vernal equinox point in this picture. So we measure from here towards this direction, and constant right ascension circles are basically celestial analog of the longitude circles on Earth. What is the prime meridian? This particular meridian, which starts from north celestial pole and goes all the way to the south celestial pole through the vernal equinox, is called the prime meridian, and right ascension is measured starting from this prime meridian. This is analogous to Earth's prime meridian, which passes through Greenwich. To be specific, 0 degree of right ascension is defined as location of Sun at midday on the vernal equinox. The other angle is called declination, which is measured starting from the equatorial plane northward or southward along the meridian of the object. So what is declination? Declination is the other angle of the spherical polar coordinate, which is equivalent to the complementary of the theta angle. Theta angle in spherical polar coordinate, we remember, we measure from z axis towards the xy plane, but here it is the other way around. We start from the equatorial plane and go towards the z axis along the meridian lines. That is, we measure declinations as angles measured from celestial equator, positive going northwards, negative going southwards along these meridian lines. So constant declination circles are basically small circles which run parallel to the celestial equator. This is basically equivalent to latitude lines on Earth. So remember this point, this will make it easier, that think of Earth's longitude and latitude and think of Earth's equator. If you extend Earth's equator, it goes over to the celestial sphere and becomes celestial equator. If you extend Earth's north and south pole to the sky, and they become celestial north pole and celestial south pole. If you extend Earth's longitude lines or constant longitude lines, they become the constant right ascension lines in the celestial sphere, and if you extend Earth's constant latitude lines, they become constant declination lines on the celestial sphere. Incidentally, there is one particular star in the sky which is nearly at the north celestial pole, and this particular star is called Polaris. Notice that the declination value for this Polaris is 89 degrees and 15 arc minutes. See, 90-degree declination means starting from the celestial equator, you are going all the way towards the north pole, because this is 90 degrees. And this star's declination value is very nearly 90 degrees. So this is very close to the north celestial pole, and that is why this star is called Polaris. Let us now discuss how Altazimuth and equatorial coordinate systems relate to each other. But before that, let us go over the pros and cons of these two coordinate systems. See, Altazimuth system is very intuitive and easy to understand. Imagine yourself standing in the middle of a ground. For you, your horizon and your body axis is pretty obvious. So setting up an Altazimuth coordinate system is obvious to you. However, standing in the middle of a ground, it is difficult to understand which way Earth's north-south axis is going or which way Earth's equatorial plane is oriented. So equatorial coordinate system is not very intuitive. However, the con for Altazimuth system is it is very location specific. That is, as the observer moves to different locations in Earth, his or her local horizon and his or her body axis keeps changing, and therefore the coordinates, the Altazimuth coordinates that he or she assigns to a star will keep changing at different locations in Earth. On the other hand, for equatorial coordinate systems, since the reference circle is Earth's equator and the reference axis is Earth's rotation axis, which is fixed for all observers in Earth, so the bottom line is Altazimuth system is easy to set up and understand, but it keeps changing for different observers at different locations, and equatorial coordinate system is fixed for all observers, but this is not really very easy to understand. It's not very intuitive, and finding the reference circle or the reference axis is itself a task. Now let us try and concentrate on this handwritten picture on the right hand side. In this picture, we have drawn the equatorial and Altazimuth coordinate systems on top of each other. So let us try and understand the different aspects of this picture. See, at the center, this blue sphere is Earth. This is the Earth's equator, and these are Earth's rotation axis. So if we extend Earth's equator to the celestial sphere, this big circle here, then we get this red circle which is the celestial equator, and if we extend Earth's axis, we get the north celestial and south celestial pole. So these are our reference circle and reference axis for the equatorial coordinate system. Now think of an observer who is standing here on Earth. For this observer, this is the horizon. So the horizontal circle for this observer is given by this yellow circle. If this guy consults a compass, he or she can identify the north direction, and facing north, his or her right hand side and left hand side will show east and west directions respectively. So standing here, if the observer faces the north, the local meridian of the observer will be the big circle connecting the north point to the south point through the observer's zenith. So in this picture, this upper hemisphere line is actually the observer's local meridian. And let us say this observer is trying to assign Altazimuth coordinate values to this particular object in the sky. For this stellar object, we need a object's meridian, which will be a big circle or arc connecting observer's zenith and observer's nadir through that object. So this is the object's meridian and this is the observer's meridian. Starting from the north point of the observer, going east direction is a positive. So we start from the north point and go along the horizon towards east to reach the object's meridian. To measure the azimuth angle, we start from the observer's local meridian, which will be the north point here, and starting from there we go along the horizon towards east and we reach up to the object's meridian, and this angle subtended by this arc at the center is the azimuth angle. And altitude of the star is pretty easy. All the observer has to do is to measure the angle starting from his or her horizon and going along the meridian up to the star. Now if we try to understand what should be the right ascension and declination for this star in this same picture, let us try and see if we can do the same. So for that we have to assign some reference point on the celestial equator, because right ascension will measure along the celestial equator and declination will measure from the celestial equator. So for this purpose, this star's meridian will be starting from north celestial pole through the star to the south celestial pole here. So I have not drawn the line in this picture, but it will be something like this. Just follow the cursor. This line, this kind of a big circle will be the star's or the object's meridian, and the reference point from where we should start measuring the right ascension will be some point on the celestial equator, which is vernal equinox. A big circle starting from north celestial pole through the vernal equinox up to the south celestial pole will be the prime meridian. So we'll measure the angle between the prime meridian and the object's meridian so that we can assign the right ascension. So basically, if you imagine that, say, this point on the celestial equator is vernal equinox, then from vernal equinox we keep going towards east and we reach somewhere here where the meridian of the star will cross the equator. So this angle, the angle between this point and this point subtended by the celestial equator at the center, will be the right ascension. And declination is pretty easy. Once we have identified the meridian through the star, declination of the object will be measured along the meridian from the celestial equator up to that star. So this will be the right ascension and this will be the declination. There are a few other important points that one has to notice. For example, the altitude of zenith is 90 degree. That is, the zenith of the observer is at a 90 degree angle with respect to the horizon of the observer. Therefore, this statement. Another important statement is altitude of north celestial pole, which is basically this angle, that is the angle that Earth's rotation axis makes with the observer's horizon. This angle is altitude of north celestial pole, and this is supposed to be equal to observer's latitude. What is observer's latitude here? In this picture, observer is standing here on Earth and this is Earth's equatorial plane. So therefore the angle between these two lines, that is angle between Earth's equatorial plane and observer's zenith line, this angle is observer's latitude, because these are big angles between mutually perpendicular pair of lines. Notice that Earth's equatorial plane and the axis of Earth's rotation are mutually perpendicular, and similarly observer's zenith and observer's horizon are mutually perpendicular. Therefore the angle between the equator and observer's zenith and the angle between horizon and north celestial pole axis are the same. This same fact can be written in another way, that altitude of celestial equator on meridian, that is the point where celestial equator cuts the observer's local meridian, right? Observer's local meridian is given by this line and equator cuts it at this point. That point's altitude will be this angle, the angle measured from horizon. Now since we already know this angle is basically observer's latitude, so, and this whole angle is 90 degrees, therefore 90 minus observer's latitude will be the altitude of celestial equator on meridian. This same thing can be written in another way, saying that angle that celestial equator makes with horizon, the same thing is angle that celestial equator makes with horizon is again 90 degree minus observer's latitude. These two lines are basically same thing written in different words. And celestial equator intercepts local horizon due east-west point. See, celestial equator is this and it crosses the local horizon of the observer at east-west point. See, at these 2 points. In this slide, we are given the latitude of Kolkata, and you can just try and verify all these statements that are written here by taking latitude of Kolkata as an example. Let us move on to the next slide. In this slide, we have an important statement that says declination maps onto latitude on Earth. This we have already mentioned in an earlier slide where we said that if we project Earth's longitudes onto the celestial sphere, they gives us the constant right ascension lines, and if we project Earth's latitudes on the celestial sphere, they give us constant declination lines. Therefore, this statement that declination maps onto latitude on Earth. An alternative way of stating this is a star of a given declination will gradually pass over the zenith of all the observers standing on Earth at the corresponding latitude circle. That is, imagine that somebody who is standing on this 19-degree north latitude circle, and if this particular star Arcturus is here, which is at 19-degree north declination, over a course of one day this star will move like this in the sky. Why? Because Earth is rotating in this direction from west to east. Therefore, the whole sky is moving around Earth's axis apparently. A star Arcturus, which is at 19-degree north declination point, this star will move over the zenith of all the observers who are standing on 19-degree north latitude on Earth. And this happens over every 24 hours. In this slide, we see the motion of stars in the sky because Earth's daily rotation. In this image, imagine a person standing exactly on the North Pole. For him or her, the zenith point and north celestial pole are the same, and equatorial plane and horizon are the same. So for this person, as Earth rotates from west to east, the whole sky rotates like this. So therefore, since all the stars are stuck on the inside surface of the sky, so stars will appear to move like this in the course of one day. So therefore, this is the kind of motion, daily motion of stars that this person will observe in the sky. If the observer moves from the North Pole to some higher latitude circle, higher with respect to Earth's equator of course, so for this person this is the zenith and this is the horizon, and since he has moved away from the North Pole, with respect to him Earth's equator has become a tilted plane, right? So for this guy the whole sky will move like this, and therefore he will see the stars to move along these tilted circles. For this person, notice that certain star will rise and fall. Some stars will be over his horizon for a shorter period of time, some stars will be over his horizon for a longer period of time, and there will even be some stars which are never setting and always over his horizon. If this person moves further south and goes on to a lower latitude circle, so for him his horizon is still the same, the horizontal plane, his zenith is here, but for him the equatorial plane is even more tilted. For this person, the stars are moving along this kind of tilted circles. So you see that the circles are more sharply angled with respect to the observer's horizon. This slide tells you how horizon delimits the portion of sky that one can or can't see at a given time of the day. Notice that, say this is the observer. So for him, notice that this is the horizon and this portion of the celestial sphere is visible to that person. So all the stars that are within this area, those stars are actually rising and setting as the sky moves around the north-south direction. So the whole sky is going around like this. So many of the stars which are going like this, follow the cursor, see the stars will rise like this and fall like this. Okay, and when the star goes below this circle, this star is actually not visible to the person because the star is going below the horizon of the person. Those stars which are within this region of the sky, they actually never set for this person because these stars are moving in such a way that they are always over the horizon of that person. So these are always visible to that person. These are called circumpolar stars. Similarly, there will be a group of stars which are within this region of the sky and moving in this fashion. These stars will never be visible to the person, or you can say that these stars are always below the horizon of this person. Let us move on to the next slide. This shows you apparent path of sun in particular. Notice that as Earth moves around its own axis in course of a day, all the stars along with the sky is rotating on specific circles in the celestial sphere. These circles are showing daily tracks of stars. Now, stars are fixed in the sky and therefore their daily circles is fixed in the sky. But since with respect to Earth, Sun's relative position keeps changing throughout the course of a year, so Sun at different times of year follow different circles in the sky. They are all parallel circles to each other, but they will be different. On March 21st, Sun's daily track is this circle in the middle. After March 21st up to June 21st, Sun's daily track will keep shifting. On June 21st, Sun's daily track will reach this limiting line. This is the summer solstice. This corresponds to the highest point that Sun reaches on northern hemisphere. After June 21st, Sun's daily track again starts to move southwards. It crosses this middle line on September 22nd and then goes down south. The Sun's daily track keeps shifting southwards till December 21st, when it reaches the lowest point in the southern hemisphere, which corresponds to the winter solstice, and then it again starts its northwards journey until March 21st. It keeps shifting, and on March 21st it again reaches this central track. This is the way Sun's apparent daily track keeps changing throughout the course of year, and this is happening because Earth's orbital rotation around Sun. So let us go over to the next slide. This slide shows effect of Earth's orbital motion on seasons. Because Earth's axis of rotation is inclined with respect to the perpendicular of Earth's orbital plane around Sun, therefore the solar illumination and the daylight hours vary at a given location throughout the year. Notice that during these two positions, Earth's northern hemisphere and southern hemisphere are equally illuminated by Sun. But when Earth moves at this position, see, northern hemisphere is tilted more towards the Sun, and when Earth reaches this position, notice that southern hemisphere is tilted more towards the Sun. See, here this axis, the north pole is tilted towards the Sun, and here the south pole is tilted towards the Sun. So therefore, during this time, southern hemisphere gets less light and northern hemisphere gets more light. During this time, it's the other way around. And at these 2 points, both the northern and southern hemisphere gets equal light from Sun. So these are spring and autumn times. This is actually summer in northern hemisphere and winter in southern hemisphere, and here it is winter in the northern hemisphere and summer in the southern hemisphere. In this slide, we are actually emphasizing the same point, that when Sun is higher in the sky during the summer, energy is concentrated and the ground heats up pretty easily, whereas when the Sun is lower, that is during the winter side, when Sun is giving light in a more tilted fashion, then the energy is more diffused. It is passing more layers of the atmosphere, and therefore ground stays comparatively cooler. Also, there are more daylight hours during the summer than there are in the winter, and therefore Sun's light is getting more time to heat up the ground. So these are the reasons for different seasons that we experience in Earth. Let us stop this lecture now, and I hope to see you in the next lecture, where we will be talking about some measurable properties of stars. Bye bye.